This podcast was created by Dr. Alyssa R. Jones for PSYC 5300 graduate level behavioral statistics using Notebook LM. The system was given specific parameters and restricted to content drawn from the assigned Crump Lab texts, answering questions with data and reproducible statistics for psychologists with R. The narration is produced using AI-generated voices. These voices do not represent recordings of Dr. Jones or the authors of the assigned materials. Although the podcast was generated from the designated course text, AI-produced summaries, explanations, and narration may still contain errors, omissions, or oversimplifications. Students should use each episode as a learning supplement and consult the assigned readings, course materials, and instructor guidance when clarification is needed.
If I hand you a completely broken, illogical argument, but you happen to agree with the final conclusion, there is a 92% chance you'll defend that broken logic as flawless. Welcome to the deep dive.
It is a profoundly humbling statistic, and honestly, it's the exact reason we're having this conversation today.
Right, because today we are talking directly to you, the graduate student who just walked into their psychology research methods course.
Probably clutching a coffee, looking at the syllabus, and seeing the very intimidating words statistical computing.
Yeah, we know exactly where you were sitting right now. You aren't new to research design. You know how to ask a good theoretical question. You've read the literature. You understand the history of your field.
Exactly.
But now you're being asked to take this massive leap into statistical computing specifically, into learning the programming language R. And that can feel, it feels incredibly daunting.
Oh, absolutely. It feels as if you signed up to study the nuances of the human mind, and somehow you accidentally enrolled in a computer science boot camp. And that is a very common, very valid feeling. But before you ever install that software on your machine, before you stare at a blinking cursor and write your first line of code, we are going on a mission.
A conceptual mission.
Right. This deep dive is designed to build your conceptual intuition. We're synthesizing foundational texts on reproducible statistics with R and really exploring the underlying philosophy of answering questions with data.
Because we want to show you exactly why statistical thinking and reproducibility are not just, hurdles to clear for your degree. They are the absolute bedrock of modern psychology.
Exactly.
I always like to think of traditional point-and-click statistical software things like SPSS or Excel as a well-meaning but incredibly forgetful sous chef.
I love this analogy.
Right, because you tell them what to chop, you tell them what to saute, and they hand you a beautiful meal. But if you ask them 3 weeks later, hey, how exactly did you make that sauce? They just shrug.
Yeah, they didn't write anything down.
Exactly. But scripting with R, on the other hand, is like having an infallible recipe machine. It forces you to write down every single measurement, every single temperature change, perfectly repeating every step, every single time.
Which really brings us to the core tension of your upcoming career. What we are talking about today isn't actually mathematics.
Right, it's not about math.
No, it is about preserving the integrity of the scientific process. To understand why we need that infallible recipe machine, we really have to look closely at the flawed hardware we all rely on every single day.
The human brain.
The human brain.
Which raises a question that, frankly, a lot of first-year researchers quietly ask themselves, but are too afraid to say out loud.
Which is?
Why do psychologists rely so heavily on complex statistics in the first place? If human behavior is observable, why can't we just use rigorous common sense to evaluate our evidence?
Well, on the surface, everyday observation does serve us well. If someone is visibly agitated, clenching their fists, you don't need a regression analysis to tell you to give them some space.
No, you just back away.
Well, exactly. We navigate our daily lives using intuition and verbal reasoning, and evolution has tuned those skills to keep us alive. But the sources we are looking at today make a really critical distinction between survival heuristics and scientific truth.
And that distinction is what exactly?
That humans are biologically unequipped to evaluate complex, abstract evidence impartially.
And this brings us right back to that 92% failure rate I mentioned at the top of the show.
Yes, it does.
Because our sources highlight this incredible study from 1983 by researchers Evans, Barston, and Pollard. They were investigating this cognitive phenomenon called belief bias.
Right.
And honestly, reading through their methodology, It absolutely shatters the illusion that we are rational, objective creatures capable of impartial analysis.
Oh, totally. And the brilliance of the Evans, Barston, and Pollard study is just its simplicity. They weren't testing people on complex statistical models or confusing probabilistic math.
No, it was way simpler than that.
Right. They were testing them on basic logical syllogisms, pure deductive reasoning. They presented participants with logical arguments where the underlying structural logic was either completely valid or completely invalid.
Okay.
And then they paired these logical structures with conclusions that were either highly believable or highly unbelievable based on just everyday knowledge.
I actually want to walk through the exact phrasing of the example provided in the text.
Yeah.
Because reading it, it actually twisted my own brain into a knot for a second.
Let's do it.
Okay, so they gave participants an argument structured like this. Premise 1, no cigarettes are inexpensive.
Okay, premise 1.
Premise 2, some addictive things are inexpensive.
Got it.
Conclusion, therefore, some addictive things are not cigarettes.
So let's break down the mechanics of that. Logically, that is a perfectly valid deductive structure.
Right.
If A is never B and some C is B, then some C is not A. It tracks perfectly.
Yeah, makes sense.
Furthermore, the conclusion that some addictive things are not cigarettes happens to be a highly believable statement in the real world.
Right, because we know alcohol, caffeine, gambling, those all exist.
Exactly. So when the structural logic is valid and the final conclusion aligns with what we already believe to be true, humans perform exceptionally well. In the study, about 92% of people correctly identified that specific argument as logically valid.
Which feels good. We like to think we're smart.
Sure, but the researchers didn't stop there.
Right, they flipped the board. They gave participants an invalid logical argument, a structure where the conclusion fundamentally did not follow from the premises.
Yes.
But, and here's the kicker, they paired that broken logic with a conclusion the participant already agreed with.
And this is the exact moment the biological hardware malfunctions.
Yeah.
When participants read an invalid, broken logical argument that resulted in a conclusion they already believed to be true, they mistakenly categorized the logic as valid 92% of the time.
92%. We literally cannot see bad logic if we like the conclusion.
We are so blinded by our desire for the world to neatly align with our pre-existing beliefs that we will completely ignore the fact that the underlying evidence doesn't actually support the claim.
The brain just looks at the final sentence, says, yep, I agree with that, and rubber stamps the entire flawed process that led to it.
Exactly. Now, I want you to overlay that cognitive malfunction onto your career as a psychological researcher.
Oh, wow. Yeah.
If you design a study, you spend a year collecting data, and the final output supports your brilliant, deeply held hypothesis, your brain is biologically primed to scream, the logic is flawless.
Even if your methodology is fundamentally broken.
Exactly.
Okay, I have to play devil's advocate here, though. Because as a graduate student listening to this, you're being trained extensively in the scientific method.
Right.
You read peer-reviewed papers all day. You're taught to be objective. So is the argument here that even the most seasoned, highly trained researchers are fundamentally incapable of looking at their own raw data without a mathematical framework to keep them honest?
That is precisely the argument. Training does not eliminate belief bias. It really just makes you better at rationalizing your biases. Statistics is not just a collection of mathematical formulas that old professors want to torture you with.
Good to know.
Right. Statistics is a psychological safeguard against ourselves. It is a tool designed specifically to bypass human belief bias.
By forcing you to establish the rigid rules of evidence before you ever look at the conclusion.
Exactly. Because we know for a fact that our brains will betray us if we let intuition evaluate the outcome.
So approaching your own mind with a healthy dose of suspicion is basically the first step in research methodology.
It has to be. Because if human intuition fails at simple three-sentence logical syllogisms, the failure compounds exponentially when we are confronted with complex aggregated data sets.
Which introduces entirely new ways for our intuition to fail.
Yes, it does. And this leads directly to one of the most famous statistical illusions in history, which is prominently featured in our sources today.
Simpson's paradox.
Simpson's paradox.
The cautionary tale of the 1973 UC Berkeley postgraduate admissions. The historical context of this case alone is fascinating.
It really is. Set the scene for us.
So the university was analyzing its admissions data, and the overall aggregated numbers showed a glaring, undeniable disparity. 44% of male applicants were admitted, compared to only 35% of female applicants.
And in a pool of nearly 13,000 applicants, a 9% difference is statistically massive.
Yeah, that's not a rounding error.
No, it's not a fluke of a small sample size. When university administrators looked at those raw numbers, their intuition screamed that this was an open and shut case of systemic, blatant gender discrimination.
It looked like the institution was actively rejecting women at the gates.
Completely. Naturally, the university was terrified of the legal and social implications. They immediately called in the statisticians to figure out exactly which departments were the worst offenders so they could address the bias.
So the statisticians took that massive aggregated data pool and they disaggregated it.
Right. They separated the numbers. They looked at the admissions data individual department by individual department.
And the result of that disaggregation completely defied common sense.
It flipped everything upside down.
When they broke the data down, they discovered that the vast majority of the individual departments actually had a slightly higher success rate for women than for men.
Which sounds completely insane.
Right. I want to make sure we're unpacking the mechanics of this because it sounds like a mathematical impossibility. Overall, the university accepted men at a significantly higher rate. But when you look at the individual departments that make up that overall number, almost every single one of them accepted women at a higher rate. How does the math actually allow for that to happen?
So to understand the mechanism of Simpson's paradox, we have to look at the denominators, not just the percentages.
Okay, denominators.
The paradox occurs because the subgroups, in this case, the male and female applicants, were not evenly distributed across the different conditions, which were the departments.
Ah, I see.
The departments varied wildly in how competitive they were. Some departments were well-funded, admitted over 60% of all applicants. Other departments were highly constrained and admitted less than 10% of all applicants.
Let's run a micro example to really cement this intuition, because seeing the invisible math is crucial for a researcher.
Yeah.
Let's invent a tiny university with just 2 departments.
Okay, that's the perfect way to model it.
Department A, which is incredibly hard to get into, and Department B, which is very easy to get into.
Okay, so let's say Department A, the hard one, accepts 20% of women and only 10% of men.
Clearly, Department A favors women.
Right. Now let's say Department B, the easy one, accepts 80% of women and 70% of men.
So Department B also favors women. In both isolated cases, women have a higher acceptance rate.
Exactly.
Okay, both departments favor women. So where does the paradox come in?
It comes in through self-selection. Imagine 90 women apply to the really hard Department A, but only 10 women apply to the easy Department B.
Okay.
Meanwhile, the men do the exact opposite. 90 men apply to the easy Department B, and only 10 apply to the hard Department A.
Oh, I see where this is going. Let's do the math on the women first.
Go for it.
90 women apply to the hard department with a 20% acceptance rate. That means 18 women get in.
Right.
10 women apply to the easy department with an 80% acceptance rate. That means 8 women get in. So overall, 26 women got accepted out of 100 total applicants. A 26% overall acceptance rate for women.
Perfect. Now run the exact same math for the men.
Okay. 10 men apply to the hard department with a 10% acceptance rate. That is 1 man accepted. 90 men apply to the easy department with a 70% acceptance rate. That is 63 men accepted.
Right.
So overall, 64 men get accepted out of 100 total applicants. A 64% overall acceptance rate for men.
And there it is.
That is incredible to see play out. The overall acceptance rate for men is 64%, and for women, it's only 26%.
It looks like massive discrimination against women on the macro level.
Yet in Department A, women were accepted at double the rate of men, 20% to 10%. And in Department B, women were accepted at a higher rate as well, 80% to 70%.
That is the exact mechanism of Simpson's paradox. The female applicants at Berkeley were overwhelmingly self-selecting and applying to the highly competitive departments.
Departments with very low acceptance rates for everyone.
Exactly. The male applicants were overwhelmingly applying to the easier departments that let in a large percentage of applicants. Because the groups were pulling from vastly different denominators, the aggregated data completely inverted the reality of the departmental data.
It's like looking at a highly pixelated image. When you look at the whole picture, the aggregated data, you see one large, distinct shape that looks exactly like institutional bias.
Right.
But when you zoom in and disaggregate the pixels into individual departments, the image completely changes. The university's admissions process, at the committee level, actually leans slightly toward women.
Which totally shifts the narrative.
But as a researcher, This raises a massive philosophical dilemma. How do you know when to stop zooming in? I mean, how does a researcher know they've found the true resolution of their data?
And that question is the philosophical crux of all research methodology. Statistics is a powerful tool, sure, but it requires deep contextual sociological thought, not just blind computational calculation.
You can't just run the numbers.
Right. The math cleared the University of systemic bias at the level of the admissions committee. The committees weren't discriminating. But, as the source material points out, resolving the mathematical paradox only opens the door to a much more profound research question.
Because the statistics answer the what, but they completely leave out the why.
Precisely. Why were the female applicants overwhelmingly applying to the highly competitive, heavily rejected departments?
Right. What was driving that behavior?
Well, historically, those tended to be the humanities and social sciences, which had less funding and fewer open spots. And why were the men applying to the higher acceptance departments? Those tended to be the hard sciences and engineering, which received massive grants and had many open spots.
Wow. So the math tells you what is happening within the confines of the data you collected. It cannot tell you what variables you failed to collect or what societal forces shaped the data before it ever reached your desk.
Exactly. Systemic bias still existed. It just existed earlier in the pipeline, pushing women toward underfunded fields.
This is a crucial lesson for anyone stepping into a research role. You can have the most powerful statistical software in the world. You can be an absolute wizard in coding GAR. But if you aren't thinking critically about the real-world context of your variables, you will generate very precise, highly significant, completely misleading garbage.
That is the perfect way to put it. Simpson's paradox shows how the natural hidden structures of the world can mask the truth in the data. But very often, it isn't the natural world that ruins the data. It is the researcher themselves.
Usually by accident.
Almost always by accident. And the text brings up this vital distinction between threats to internal validity and threats to external validity, framing it around confounds and artifacts.
Let's define those terms clearly, because they will govern every experiment you ever design as a grad student.
Definitely. Internal validity is the extent to which you can confidently claim that your independent variable, the thing you are manipulating, is actually what caused the change in your dependent variable.
Rather than some outside force.
Right. And that outside force is a confound.
Right, a confound.
A confound is an unmeasured variable that happens to be related to both your predictor and your outcome, making it impossible to separate the true cause.
So, for example, if you observe that people who smoke heavily have higher rates of lung cancer, a critic might point out a confound.
Exactly. They might say perhaps heavy smokers also tend to have poorer diets, or maybe they work in more hazardous industrial environments.
So the diet or the environment is the confound. It threatens your internal validity because you don't know if the smoking caused the cancer or the bad diet caused it.
Correct. And the natural response of a researcher trying to achieve perfect internal validity is to control the environment.
Lock it down.
Right. The text uses a hypothetical, highly controlled experiment to illustrate this. Let's say a researcher wants to definitively eliminate all those confounds regarding smoking and cancer.
Okay.
They take a group of perfectly healthy subjects, lock them in a perfectly sterile, controlled lab facility, feed them the exact same nutritionally complete diet, ensure they have zero environmental hazards, and then require half of them to smoke heavily.
From a purely mechanical standpoint, that researcher has achieved perfect internal validity. They have completely controlled the environment and eliminated the confounds of diet and environment.
Exactly. If the smoking group gets cancer, the researcher can say with absolute mathematical certainty that in this specific environment, smoking was the cause.
But let's say the researcher runs this highly controlled experiment, and the smoking group does not develop cancer at a higher rate.
Right.
The researcher concludes smoking does not cause cancer. Why did they get that result? Well, because in the real world, maybe smoking only triggers cellular mutation when it is combined with the physiological stress of a poor diet.
Yes.
By locking the subjects in a pristine lab and giving them perfect nutrition, the researcher inadvertently created a biological situation that does not actually exist in reality.
And that resulting data point is what we call an artifact. An artifact is a threat to external validity.
External validity asks, can I generalize the results of this study to the real world?
Exactly. An artifactual result only holds true in the highly specific, artificial, sterile conditions of the laboratory. It is utterly useless outside of those walls because the real world is inherently messy.
This presents an almost impossible dilemma for the graduate student designing their first experiment.
It really does.
If you tighten your lab environment perfectly to eliminate every single confound chasing that pristine internal validity, don't you essentially guarantee that you will create an artifact? The perfectly sterile lab looks absolutely nothing like the chaotic environment where human psychology actually operates.
You have just articulated the eternal tightrope walk of experimental psychology. As you increase internal validity by rigidly controlling the environment, you almost invariably decrease external validity because you are stripping away natural context.
It is a constant, unavoidable trade-off.
It is. This is exactly why a single study rarely proves anything in psychology. Researchers must rely on a triangulation of methods mixing highly controlled lab experiments that isolate variables with messy, real-world observational studies that capture natural behavior.
Sometimes, however, a researcher thinks they are controlling the environment perfectly, but they are actually the one contaminating it.
Oh, this is my favorite part of the text.
Right. There's no better illustration of this than one of the most famous cases in the history of psychology, Clever Hans.
The famous horse from 1907 that could supposedly perform complex mathematics.
The story is just incredible. Hans and his trainer, Wilhelm von Osten, were an absolute sensation in Germany. People fully believed Hans possessed human-level intelligence.
I mean, you could ask the horse, what is the square root of 16? And Hans would tap his hoof exactly 4 times.
He could do fractions, he could track the calendar, solve musical tones, and it wasn't just a cheap circus. Trick scientists and professors evaluated Hans and were entirely baffled.
Right, because they tested him without his trainer present. They tested him with different people asking the questions, and Hans consistently got the answers right.
The scientific community was on the verge of accepting that equine intelligence was vastly misunderstood.
Until a psychologist named Oscar Funkst approached the problem methodologically.
Right.
He didn't just ask if the horse could do math, he asked what variables in the environment might be cueing the horse.
Funkst's methodology is a masterclass in isolating variables. He started manipulating the exact conditions of the questioning. First, he put blinders on Hans so the horse couldn't see the person asking the question.
And when Hans couldn't see the questioner, his mathematical abilities completely vanished.
Just gone.
Gone.
Then Funkst removed the blinders, but he had someone ask Hans a question where the questioner themselves did not know the answer.
Right. So, for example, the person would look at a number written on a card without reading it and ask Hans what the number was.
And once again, Hans failed completely.
Which is when Funkst realized that Hans was not doing mathematics at all.
No. Hans was an incredibly observant animal who had learned to read the subtle, microscopic, unconscious physical cues of the human asking the question.
The mechanism of this communication is fascinating, largely because the humans were entirely unaware they were doing it.
How exactly did it work?
Well, when a human asked Hans to add 5 and 5, they knew the answer was 10. As Hans began to tap his hoof 1, 2, 3, the human questioner's posture would naturally tense up.
Their breathing would change, their facial expression would subtly shift in anticipation of the correct answer.
And the moment Hans tapped for the 10th time, hitting the right number, that internal tension in the human broke. The questioner would relax slightly, maybe exhale, or slightly lower their head.
Exactly. Hans simply learned an incredibly effective operant conditioning loop. Keep tapping my foot until the human in front of me exhales and relaxes their shoulders. Stop tapping and I get a carrot.
It had absolutely nothing to do with math.
Nothing. It was an astonishing display of animal observation, but a complete failure of the initial researchers' methodology.
This is the ultimate example of experimenter bias, specifically a demand characteristic. The researchers' own psychological expectations were unintentionally communicated to the subject, completely invalidating the results.
If Funkst hadn't systematically altered the experimental conditions, using blinders, varying the distance, and ensuring the questioner was aligned to the answer, the initial researchers would have gone down in history as the scientists who proved horses can do arithmetic. The story of Clever Hans serves as a really stark reminder of how fragile data really is. You have to protect your experiment from environmental confounds, from laboratory artifacts, and from the unconscious arch of your own eyebrows.
Yeah, you really do.
But the reality of modern research gets even more complicated.
It does.
Because even if you design the flawless experiment, even if you perfectly balance your confounds and ensure your internal and external validity are pristine, the way you handle the resulting numbers after the experiment is over can completely ruin the science.
And this brings us to the dark side of data analysis, the practices that occur not in the laboratory, but at the computer desk.
The text dives into deceptive analytical practices that have plagued psychological research for decades. We're talking about post hoc hypothesizing and the pervasive issue of data mining, often referred to as p-hacking.
To understand why this is such a massive issue today, we really have to look at the evolution of statistical computing.
Okay, take us back.
50 years ago, running in ANOVA an analysis of variance, which compares the means of different groups to see if they are statistically different, that took significant manual time. Calculating a multiple regression was a laborious chore.
You had to really want to know the answer.
Right. Because the computational cost was so high, a researcher had to have a very strong, predefined theoretical reason to run a specific test.
You weren't just crunching numbers for the fun of it. You formed a hypothesis, you collected the data, and you ran the specific math required to test that one hypothesis.
Exactly. But today, the computing power sitting on your laptop is staggering. With modern software, you can run thousands of statistical tests in a matter of seconds.
Seconds.
You can ask the software to correlate every single variable in your massive data set with every other variable simultaneously. And the sheer computational ease leads directly to data mining.
Let's define data mining or key hacking for the listener who is about to start analyzing their own thesis data. Let's say you run your study. You test your primary hypothesis, and the result is negative.
Nothing happened.
Right. The natural temptation is to avoid throwing away all that hard work. So you start aggressively crunching the numbers in your data set, running every possible comparison, looking for anything that crosses the magic threshold of statistical significance. You keep shaking the data tree until a shiny apple falls out.
And I want to pause and explain what that magic threshold actually is, because understanding the p-value is central to understanding why p-hacking is so destructive.
Good idea.
In psychology, we generally use a p-value threshold of 0.05 to determine statistical significance.
Okay.
Conceptually, this means that if your experiment actually had no real effect, if the null hypothesis was true, there is only a 5% probability that you would see the results you got purely by random chance.
It's a built-in error rate. We accept that 1 out of 20 times, random noise will look like a real pattern.
Precisely. Now, apply that 5% error rate to data mining. If you use your computer to rapidly run 100 random exploratory correlations on your dataset without a guiding hypothesis, the laws of probability dictate that you will find, on average, 5 statistically significant results purely by random chance.
Wow.
They are false positives. They mean absolutely nothing.
It's like someone shooting an arrow at a blank wooden fence. It lands wherever it happens to land. Then the person walks up to the fence, takes out a bucket of paint, and carefully paints a bullseye right around the arrow.
Yes.
They bring their colleagues over and say, "Look what a master archer I am. A bullseye on the first try."
That is the perfect analogy for post hoc hypothesizing. The researcher mines the data, finds a random chance correlation, a false positive, and then goes back and writes the introduction to their paper as if they had predicted that exact outcome from the very beginning.
They paint the theoretical bullseye around the random arrow.
Right. It is fundamentally deceptive. It turns exploratory noise into foundational theory, and it severely damages the credibility of the entire field.
And the damage doesn't stop with that one researcher, because this behavior feeds into a systemic crisis known as the file drawer problem, or publication bias.
Yes, the file drawer problem. Academic journals are driven by novelty and significance. They want to publish exciting, statistically significant findings that push the field forward.
Naturally.
Right. But they very rarely publish null result studies that conclude, we rigorously tested this idea and absolutely nothing happened.
So imagine 20 different researchers at 20 different universities around the world, all testing the exact same hypothesis.
Okay.
Let's say the hypothesis is actually false. 19 of those researchers run the study, find no effect, get rejected by the journals, and toss their data into their filing cabinet.
The file drawer.
Right. But the 20th researcher, purely by statistical chance, that 1 in 20 probability we discussed, gets a false positive. Their data shows a significant effect.
The 20th researcher writes up the paper, submits it, and the journal publishes it. The rest of the scientific community reads this published paper entirely unaware of the 19 rigorous, failed attempts sitting in file drawers around the world.
The published literature becomes a completely skewed representation of reality.
We end up building massive theoretical frameworks on a fragile foundation of statistical anomalies.
When you lay it all out like that,
Right.
it feels incredibly daunting. We've established that humans are inherently biased and will defend bad logic if they like the conclusion. We've seen how aggregated data can mathematically lie to us through Simpson's paradox. We've explored how we can unknowingly create laboratory artifacts or subtly cue our subjects like clever Hans. And we've uncovered how the pressure to publish can lead to data mining, p-hacking, and painting bullseyes around random noise.
It sounds like a system destined to fail, doesn't it?
If I am the graduate student listening to this, sitting in the lab at 2 a.m. with a thesis defense looming and a data set that just isn't cooperating, I am wondering how any science ever gets done correctly. The temptation to just point, click, and p-hack my way to a degree feels overwhelming.
And that feeling of overwhelming temptation is exactly why the scientific community is undergoing a massive paradigm shift. This is the entire reason why reproducibility matters.
Right.
And it is the specific reason why your professor is requiring you to learn statistical computing with R instead of allowing you to rely on standard point-and-click software.
We finally arrive at the software itself, the solution to the dark side of data. Let's contrast the experience of using point-and-click software, like SPSS, with the experience of scripting in R.
Okay. When you use a graphical user interface, a drop-down menu, to run a statistical test, the software acts as a black box. You highlight your columns of data, you click a button that says Run ANOVA, and the software spits out a beautifully formatted table of results.
The forgetful sous chef hands you the meal.
Exactly. But consider the implications for reproducibility. 6 months later, when a peer reviewer wants to verify your work, or when you want to repeat the exact same analysis on a new set of data, you have no permanent record of the specific sequence of clicks you made.
Did you manually exclude 3 outliers before you clicked Run?
Yeah.
Did you transform a skewed variable? Which specific settings did you toggle in the submenus?
You don't know. You cannot definitively prove what you did to the raw data. Point-and-click environments make it incredibly easy for data mining and post-hoc tweaks to hide, either intentionally or accidentally.
But R operates on an entirely different philosophy. R does not have those drop-down menus. R relies on scripting. You are writing commands directly to the data structure.
Right. And to understand the power of this, the text provides a great historical anecdote regarding the mathematician Carl Friedrich Gauss.
Oh, I love this story.
When Gauss was a young boy in school, his teacher supposedly wanted to keep the class busy and quiet for a long time, so he instructed the students to add up all the whole numbers from 1 to 100.
The teacher expects them to sit there for an hour going, okay, 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10.
Exactly. But Gauss walked up to the teacher's desk a few minutes later with the correct answer, 5,050.
How did he do it?
Gauss didn't do the manual iterative calculation. He visualized the problem structurally. He imagined 2 number lines, one going from 1 to 100.
Okay.
And underneath it, another going backward from 100 down to 1. He realized a pattern. If you add the columns vertically, they all equal 101. 1 plus 100 is 101. 2 plus 99 is 101.
Oh, because there are 100 columns, that is 100 times 101, which equals 10,100.
Right, and then you just divide by 2 because you doubled the sequence and you get 5,050.
That is brilliant.
Gauss used an algorithm. He found a structural, repeatable rule to solve the problem instantly. When you learn R, you are learning to apply algorithms to data frames. You are stepping away from interacting with a user interface, and you are stepping into direct manipulation of the data structure itself.
And while we aren't going to teach you our syntax right now, your lab instructor will handle the actual mechanics of writing code. The conceptual shift is what matters here.
Yeah.
In R, your data lives in structures called data frames. You write a line of code to import the data. You write a line of code to filter out the outliers.
You write a line of code to run the specific InnoVA you planned from the very beginning.
This is the crucial psychological and ethical shift for you as a researcher. When you write a script in R, you are not just crunching numbers. You are creating a transparent, permanent, unalterable audit trail of your entire analytical thought process.
You are leaving a flawless trail of breadcrumbs from the raw data to the final conclusion.
A script proves to the scientific community exactly what was done to the data. If you drop a variable, there is a line of code declaring that you dropped it.
If you run 50 different exploratory tests before finding a significant one, there are 50 lines of code showing that you mined the data.
The script eliminates the shadows where p-hacking hides. It forces absolute honesty.
More importantly, it allows anyone in the world to take your raw data, run your script, and generate the exact same results. That is the very definition of reproducible science.
So for you, the graduate student sitting there feeling intimidated by the idea of opening R for the first time, change your framing. Do not look at R as a scary, complex mathematical programming language. Look at it as a diary of your scientific decisions.
I love that. A diary.
You are simply writing down the exact recipe of your thoughts, step by step, so that anyone in the world can bake the exact same cake. You are not learning to code just to get a grade. You are learning to code to protect the integrity of your science from your own human flaws.
It is a profound transition. You are shifting from being a passive consumer of knowledge to becoming a responsible, rigorous creator of knowledge.
Over the course of this deep dive, we've gone on quite a journey. We started by acknowledging the innate biological flaws of the human brain, our susceptibility to belief bias, and our tendency to defend broken logic if we like the conclusion.
We navigated the mathematical illusions hidden within aggregated data, tearing apart Simpson's paradox to see how shifting denominators can completely distort reality, and why statistics requires deep sociological context.
We explored the dangers of sloppy experimental design, contrasting internal confounds with external artifacts, and saw how easily a researcher can unwittingly cue their subjects, like clever Hans.
And we stared into the dark side of data analysis publication bias, the file drawer problem, and the overwhelming temptation to p-hack and paint the bullseye around random noise.
All of which led us to the solution, adopting scripting, specifically in R, as the ultimate tool for transparent, reproducible, and honest scientific inquiry.
Before we sign off, I want to leave you with one final thought from the source material that ties this entire philosophical journey together. Buried in the text's discussion of experimental confounds is a brief mention of the placebo effect.
Ah, the ultimate demand characteristic. We all know what it is conceptually. You give a patient a completely inert sugar pill, you tell them it is a highly advanced, powerful medicine, and the patient actually physically improves. The sheer psychological belief that they're being treated causes a biological healing response in their body.
It remains one of the most astonishing, deeply mysterious facts of human biology. The mind's expectation becomes physical reality.
It is incredible. But think about the symmetry here, connecting all the way back to our very first topic on belief bias. If the human mind's mere belief is powerful enough to physically cure the body of an ailment, and simultaneously powerful enough to utterly blind us to broken logic, then learning statistical computing is not just some technical hoop you have to jump through for a master's degree.
No, it isn't just about passing a class or making a graph.
It is the only way to outsmart the incredible, deceptive, awe-inspiring power of our own minds. So when you open R today and you face that blank, blinking cursor, take a deep breath. You are learning the language of truth in a very messy world. Go write your recipe. We believe in you.
Good luck with the lab.